methods work for simulation of nuclear processes. Many of you delivered the report, software or simulation report. Part of you is pending. Please then during the next days, during this week, it would be great if you could deliver, because it is a part of your whole result during this semester. Good. As I said, in this day, or in this chapter, today we are going to start with a completely new chapter and business as usual. Remember, first we are going to see what the topic first is, and we are going to discuss. Somebody has arrived. We are going to discuss first the theoretical background and the theoretical aspect, and then it will be taking time, probably for the whole today, would be the theoretical basis. And then during the next hours, that means next week, we're going again, like during the last sessions, we are going to apply a new computer code and for topics which are going to be discussed today. So the topic is, as you see here, then physics of nuclear fuel and irradiation behavior. You remember the reactor here looks like here, this design at the right-hand side. So, and fuel elements or fuel is loaded inside the core, and the reactor is operated for years or many months. And then because of the production of, or because of the fission processes, burning processes, different nuclides are produced, which have completely different physics and nuclear characteristics. So again, the processes are burning, for example, or fissioning due to fission processes, or activation, because we have a neutron field, neutron population inside the reactor or around the reactor, and any material existing inside the reactor would be irradiated, and nuclear activation processes would be taking place, and with the result, you have activation results or activation products with different half-life, with different decay characteristic, or emissions, and so on. And part of the materials or activated material produced inside the reactor have a very high level of activation, and consequently they have to be processed accordingly. And the big topic in this case would be the characterization of the waste produced, and we have heat producing waste, everything with the fuel, because you produce actinide and partly fission products and so on, heat producing waste, and the other groups mainly as a result of the activation would be mainly the activation of the structure, components, and so on. And every individual type of the activated material needs its own processing and treating. So for this reason, we are going to work on this topic. It is the continuation of the same topic or we saw during the last semester, you remember, but it would be more, expansion of it. That is one aspect. And the other aspect is we're going to see all problems cannot be solved by the methods we discussed during the last semester, and we need for in this field methods, mathematical methods, and we need here then numerical methods, we need computer software packages, and we're going to see how they work and how these structures are. So, okay, and first point is, you see here some example, some here facilities. At the top left-hand side here, for example, you see the individual spent fuel elements here stored in a permanent storage with a repository, for example. Here, every container here consists of many fuel elements, and the fuel element partly have not been conditioned or processed. And it is called direct storage of the fuel element. Again, this is everything heat producing waste. So at the right-hand side here, you see, for example, here the repository discussed in Germany called Gorleben, and it has first it was decided to use this facility or this repository for spent fuel element and for radionuclide, but the decision of the government has been changed, and first a big very comprehensive scientific study should be performed in Germany for different sites and different repository. That means decision on this side is depending, is not very sure. Or here at the bottom left, you see here some reprocessing facility, reprocessing because spent fuel element coming from from the reactor core contains partly unused, undepleted fuel. By reprocessing, part of them could be separated and used for different purposes for energy production, nuclear technology range. And here in France, you see, for example, reprocessing facility in France. Everything has to do with spent fuel element or activated material. So the question is, it is not so that reactors which have been operated for a long time, the fuel elements or radioactive material can be extracted from there or unloaded and directly disposed of in such facilities. One has exactly to know the characteristic of the waste, and it depends on the category of and the type of the, I said before too, of the waste. So, but the source for waste is again the reactor core, because in the reactor core, the fuel elements and structure will be irradiated, and consequently activated material will be produced. So here it is an example, a very typical example for the operation of a reactor with fuel elements. That means fuel elements are loaded inside the core, and they are irradiated in, we say, cycles. Every cycle something like 2 years, and after 2 years, because the contents of the fuel available for fission and so on would be reduced, and they have to replace by fresh one. And the question arises first, what is the composition of the spent fuel elements, or spent nuclear fuel. You see here in the form of a graphic here, for example, if you consider 1 tons or 1,000 kilogram spent nuclear fuel, is still at 2 years operation, it contains still 955 kilogram uranium. But we should keep in mind that the big part of the uranium is not fissionable one, and that means it is not uranium-235. But anyhow, in 955, the big part is something like 3.3% is still, or maybe 2%, depends on the mode of the operation. The big part is uranium-235 available for extraction and use too. And we produce during the operation or irradiation a considerable amount of plutonium here, which is partly considered as fuel and partly considered as your waste, depends. So, and in the whole range of the waste or radioactive material which are produced, one group is called here minor actinides. And minor actinides, they have normally very long-term half-lives. Here, for example, neptunium-237, 0.5 kilogram of 1,000 kilogram. And then here, curium, for example, 0.02 kilogram. And again, the half-life of these minor actinides are very, very long, and it is very sensitive, important for repository for long-term disposal. So, and then next package we have as a result of the fission, remember we produce fission products like here iodine, technetium, zirconium, cesium, and so on. And these fission products are normally gamma emitters, but the half-lives are not so long like in case of minor actinides or partly actinide. Anyhow, in the range of 200 years or 300 years. And finally, we have here short-lived fission products. So in this case, cesium again, and strontium here, and the amount is 1 kilogram compared to the total mass of the spent nuclear fuel. Partly as a result of the activation, burning, fissioning, and so on, stable isotope would be produced, for example, lanthanides and other stable materials. So, and you see here in this cylinder here, and the green part is still uranium, unused uranium existing in the spent fuel element or fuel. So, and every individual nuclide, radionuclide, has different characteristic, different behavior with respect to the decay, with respect to neutron, with respect to heat production, and so on and so on. For this reason, during the operation, I should say, all those radionuclides, as we saw here, by minor actinide or fission product and so on, are produced during the operation of a reactor. So even the activation of the structural material, that means the responsible effect or reason is the operation of the reactor, as we saw in the beginning, for example, in this picture. So now, because we have to distinguish between two phases. Phase one, during the generation, for example, during the operation of a reactor, and then during that phase, then nuclear radionuclides are produced. And for the phase after shutting down the reactor, that means no production is made because of the irradiation. And everything takes place because of the decay process. Of course, because of the decay process, some new radionuclide would be produced too. Depends on half-life and so on. And I said every individual nuclide has its nuclear characteristic. For this reason, it is not possible, not correct way to go the lumped way. That means to put all radionuclide and say it is plutonium, and we can dispose of in somewhere. And we have to distinguish between the individual one and first amount of it, and then with respect to activity and with respect to heat or radiation emission and so on. This picture or this figure shows very clearly what happens, what kind of radionuclides are produced during the operation of a reactor. And you remember we have normally, if you take pressurized water reactors, we have normally uranium fueled or material. So that means fuel consisting of uranium-235 and uranium-238, because uranium ore is mainly consisting of uranium-238, something like 99.3%. But for operation or loading or using for fission processes, first the enrichment has to be increased from 0.7% for uranium-235 to 3.5% or in case of boiling water reactors or in case of pressurized water reactors. Good. But you remember fission is mainly made in uranium-235. That means the big loss term is coming because of fissioning of this isotope of the uranium. So uranium-235 absorbs neutrons, and you go on this arrow here and goes, of course, to uranium-236. And uranium-236 has a very big or long half-life, and it is an alpha emitter, yellow, and then it absorbs one neutron inside the core during the whole cycle, goes to uranium-237, is beta emitter, has a very short half-life, something like 1 day, and then it decays because of disintegration. It goes to neptunium-237, and 237 is an alpha emitter. It is mainly that is the case mainly for actinides, and this comes to neptunium-237, and by absorbing a neutron goes to neptunium-238. But absorbing, and it decays too after some days, 2 days, it goes to plutonium-238, and finally, by absorbing a neutron, this arrow to right-hand side, we get plutonium, and it is a new fuel. It was originally not existing inside the core, reactor core. So, and in this channel, or in this path, neptunium-238 goes to neptunium-239 by this case absorption of a neutron, and it is a short-lived actinide and goes to plutonium. That means we have two passes to come to plutonium-238. plutonium-239, and that means plutonium-239 now as fissionable material. It is comparable with uranium-235, more efficient one, is now existing in the fuel during the operation, not initial. So, and then it goes to, by absorption to an neutron, goes to plutonium-40, 240, and then to plutonium-41, 89, and beta emitter, it goes to americium-241, and it is minor actinide, and you see alpha emitter, and has something like 430 years half-life. It is going to americium-242, it is beta emitter, it decays to curium-242, and you see here it is short-term, 162 days, and it absorbs neutron and goes to curium-243 as a minor actinide with 280 years and its half-life. Finally, curium-244, the long-term too, and at the end of this channel, you find here curium-245 with 8,500 years half-life. And for this reason, for repository or final disposal, the minor actinides are very, very important. That is only a table of the transuranic elements as a result of the fission product, decay product, and so on. Good. Now, I said before too, every individual nuclide in this chain, in this table, in this process, has its own characteristic and behavior. For this reason, the big work, big job is to determine the composition first of the fuel and the concentration of the individual one. From the other side, from nuclear investigations side, we know if we have uranium-2, for example, plutonium-240 or 239, we know it is an alpha emitter and so on with respect to the waste management and impact and so on, and it can be combined with the inventory and analyzed for safe disposal and so on. Good. Now the question is, what happens with the individual nuclides? That is the point, and how they would be formed or generated, and what is the source, and what is the concentration. You remember from the first semester, first point is, if we take the very standard fuel consisting of uranium-235 and mainly uranium-238, first point is, as we saw in the chart too, because of and beta emission, it goes to neptunium-239, and finally it goes to plutonium-239. I said before too, it's a fissionable material by capturing neutron, going to plutonium-240 and going to 41 and 242. That was really the chain here, starting with uranium-235 as big part of the fuel. So this means for every individual nuclide, we have to write a balance equation for the production and for the loss. And production is mainly because of some captures or decay of other precursor, for example, and decay is, lost term is mainly because of decay and depending on half-life. So in case of the first step, in case of uranium, for example, if you take the fresh fuel, mainly consisting of uranium-238, and the starting nuclide is uranium-238, and its consumption or change of the composition or change of its concentration can be determined by writing a differential equation. And you see here, the first equation exactly describes the differential equation or its balance equation. The left-hand side is the rate of the change of this concentration of this nuclide, uranium-238, per second, you see ET. And at the right-hand side is only a loss term. Loss term because we don't produce any uranium-238. It is from the loaded into the core at the initial phase, from the beginning. For this reason, it has only the loss term. And remember, loss term because of the capturing neutron. And now here right-hand side is the reaction rate or capture rate or absorption rate. You see here cross-section or capture, neutron flux at the position where the fuel element is. And here is the number density of this nuclide. So you can imagine it is very simple to solve it because it is the only variable or only function existing at the left-hand side, right-hand side is uranium itself. Of course, this is an approximation because we're going to see maybe, here, it is during the time operation, for example, everything would be changing. This balance equation or differential equation is very simply solvable if phi, that means neutron flux at the position of this fuel element or this fuel radionuclide is constant. So otherwise, one has exactly to put here correct function for neutron flux, and from the other side, it depends on the actual composition of the fuel. But for the first approximation, for example, for the analytical solution of the problem, one can assume a phi has an average value, a mean value during the whole irradiation. Anyhow, under these conditions, we can solve this one and you get the change of the concentration or number density uranium-238 as a function of time. So for I go maybe in order to see why phi during the operation is not a constant value, and under real condition, one has to consider it, and we can see it from the next diagram here. And you see here the distribution of the thermal neutron flux. So in a reactor, for example, here you see this cylinder at the bottom, it is a fuel element. So from the bottom to the top, so depends, and then you see under some given condition, one moment please. Yeah. You see here again the whole length of a fuel element starting at 0, and that is the final position, normalized 1. It can be 4 meters long, and you see, and here solid line is the neutron flux distribution under given condition. And here the dashed curves are for other position of the shutdown system, for example. You can imagine during the start of a reactor, the core contains a big amount of fuel. So, and consequently, the multiplication factor is very high. So, but this multiplication factor is very high. It has to be compensated by shutdown system. For this reason, the shutdown system is inserted inside the reactor in order to control the operation. And if the shutdown system or the absorber system is mainly inserted inside the reactor, the neutron flux would be shifted. The maximum of the neutron flux would be shifted to the bottom, to the lower part of the reactor. You see here in this picture very clearly, for example, this dashed line is the maximum at 0.8. That means 80% length of the whole length of the fuel element. That means if the absorber system is positioned inside the reactor up to the bottom of the reactor or second half of the reactor, then the neutron flux at the upper part of the reactor, because of the absorber system, would be lower. You see here this dashed line. It means the flux has lower value. And at the position where is free of any shutdown or absorber material, the neutron flux goes higher. In other words, by moving the control rods or absorber rod to the bottom, or the control of the activity, the neutron flux is pushed move to the lower part of the reactor. That means the flux distribution inside the reactor at the initial phase of a cycle, operational cycle, gets such a shape. You see, the maximum is at the lower part of the reactor. So, with the operation of a reactor, of course, the fuel is consumed because of fission process, absorption process, and so on. That means the control rods have to be removed, partially removed from the reactor core. That means at the end of a cycle, for example, the big part of the control rods are staying at the upper part of the reactor core, and you see here the solid line, and the reactor neutron flux or power distribution gets a symmetrical shape because there is practically no effect of the absorption by control rod because they have been practically removed from the reactor core. What I am saying with this diagram is typical for the operation of a reactor, nuclear reactor, during the cycle is a very significant change of the neutron flux shape. Again, at the beginning, like this dashed line, and at the end of cycle is symmetrical. And for this reason, I said here in case of this balance equation, for the calculation of the concentration of uranium-238, we assume, or it can be analytically solved if we apply a constant flux. But you see, during the operation, it is not the case. The flux shape would be changing. And it is very complex to go the analytical way and determine for time-dependent flux. For this reason, it uses here, or normally numerical way, is taken, and then can be step by step solve the problem and determine what is then concentration of uranium-238 at every time step during the cycle. Good. Okay, that is the starting point for the main part of the fuel, uranium-238. So then you see here, it captures a neutron, I said, and emits beta. The result is Neptunium-239. For this one, we can write a differential equation here, balance equation. Left-hand side is the rate of the change here, and then right-hand side is production term and loss term. You see here, this production term is exactly the last term of uranium-238. Everything, every amount of in the last term for uranium-238 is the production term for neptunium. You see, then on this pass from the uranium-238 to neptunium. And the other one, because neptunium-239 is a radionuclide, is a given half-life, is a given or very characteristic decay constant, lambda here, that would be then the activity, that means the loss term. So now you see here very clearly, this differential equation is only solvable if we know the time function or the function uranium-238. Then we have, only in this case, we would get a differential equation which is a function or is only for neptunium. So, but the answer to this question, what about uranium-238, is very simple, very easy, because we solve it in the previous step. Here we solved it, and if you solve it, you can insert the solution in this part of the equations, and then finally this whole equation can be solved numerically or analytically. So the next step is plutonium-239. You remember, and then in this case is the balance equation similar. Left-hand side, all the time the derivation to time that we change in 1 second of the concentration. And here, everything what we lose in the previous step is plus term or production term for that one. And plutonium is, here in this case, mainly a neutral absorber, because the cross-section is very high. For this reason, in this case, the loss term of plutonium-239 is not because of the decay, mainly because of the absorption of a neutron. And you see in this chart here too, you see from plutonium, by capturing neutron, that means C, sigma C, it goes to plutonium-240. And you see in the next equation, that would be plutonium for 240, and you see in the next term, or next term here, then last term of the plutonium-240, here's the same because of the capturing neutron, and production term is coming from previous one, that means previous case, and it would be the production term. And here is the same, that means plutonium function as a function of time can be obtained from here, put here, and then it can be solved. That means step by step, first uranium-238, then putting here, getting the solution for neptunium, putting solution for neptunium, and putting in this equation, we get plutonium-239, and so on. And finally, if you continue this way or this procedure, then at the end, you would find the final step and the final the nuclide, for example, plutonium-241, and so on. Good. So that is again, this chart shows only, this is a schematic one, it shows only what nuclides are produced, and then by what ways, and then here is the mathematical way, again, to describe the change or change of the concentration of the individual. So then, what is the consequence of a neutron flux? We know the effect. Now, here we have, I said in the beginning too, we have to distinguish between operational time during the operational cycle and after shutting down or preprocessing or storage, and later on for long-term storage, for example. So we have to distinguish between two phases. During the operation, it is very important because all radionuclides are produced during that phase. And what is the effect? From the operational point of view, is very important multiplication factor. Otherwise, if you don't know how big it is, how it is changed, it is not possible to operate a reactor because shutdown system has been designed according to the change in multiplication factor due to the fission and due to absorption, any changes in the design of the system or operation of the system. So, and you remember the multiplication factor in very general case consists of 6 factors, here into epsilon P, and then PF, PTH, PF, and so on. So every individual one depends on the condition, neutronic condition, operational condition in the reactor itself and inside the reactor. For example, leakage term would be changing. So, or here, absorption in the fuel itself. I said before too, flux would be changing, and consequently, absorption term would be changing. Or in absorption in the structural material, because part of the neutrons produced inside the reactor would leave the system and go into the surrounding structure, and they would be absorbed there and is considered as loss term. Or during the operation of a reactor, I said before too, some fission products are produced, and the fission product, part of them has very high absorption cross-section, like a source for neutron absorption. And xenon or samarium are examples. And then one has to know exactly how big is the amount of this neutron strongly absorbing fission products. And the next one is other isotopes, uranium-236, uranium-237, plutonium, and so on, because you remember the chain reaction, or this one, and all individual isotopes here. For example, if you take plutonium-238, it is a beta emitter, goes to plutonium-239. In every state condition, for example, here, as neptunium-238, it has some cross-section or neutron absorption. Consequently, multiplication factor can be slightly changed by this radionuclide. And this is true for all individual radionuclides with their nuclear characteristic, cross-section, for example. For this reason, absorption in higher isotopes means in neptunium, plutonium of different mass numbers. So, and absorption in the absorber rods, for example, for the control of reactor. Part of the neutrons are produced and absorbed, produced in the fuel and absorbed in the absorber material. And this has some effect on multiplication factor. So, very important is in this listing is again, we produce a lot of different radionuclides with different characteristics for optimum operation of the reactor and material balance. We have exactly to know what the composition or the composition and concentration of the individual one is. So this change in multiplication factor, you remember? It is practically the same like we saw before. You remember multiplication factor can be changed, and the change to 1, because 1 is the case which is the critical condition. And it's called reactivity. You remember from the last session? Yeah, that is rho at the top. See here at the top. And this is then the reactivity unit and so on, you know, and you don't need to discuss about it again. Delta K, change of multiplication factor, you remember that would be the difference to 1. So now that was only additional information from the past. Okay, now if we concentrate our attention to one point, the main fissionable material, uranium-23805, it absorbs 1 neutrons and it has then the compound nucleus, the result, has 2 ways because it is still unstable and has 2 ways. One is the fission way and the other one is N-gamma way. That means the compound nucleus emits gamma and goes probably from the to stable condition. So these 2 ways are completely different. And in the first case, upper case, we get fission products. In the other case, we get uranium-236. And this absorbs, again, neutron and goes to uranium-237. In case of uranium-236, it is very clear it is not fissionable. For this reason, we don't have here not 2 branches, only in case of uranium-235. So that is one aspect. The other aspect is reaction rate. Reaction rate means the fission rate. That means for uranium-235. And you see here, if you neglect here's integral sign here, you see phi, neutron flux, multiplied by fission cross-section, multiplied by concentration, number density, Phu, then this product here, this 3 terms, would be then fission rate. And because everyone depends on the energy, one has to integrate to find the sum for all energy points. So that would be reaction rate or fission rate. But now, again, the same equation. So in this one, the same equation. Now, how we can determine the individual one, individual solution. First, uranium-235. Remember, we say designate it, we call it N1. because this is the initial nuclide. And in this case, we have on the last term absorption. You see, by absorption, that is the absorption rate. And this absorption contains or is the sum of the capture here, absorption, plus fission, because every pass, the upper one, lower one, goes to the loss of uranium-235. For this reason, A here. So, and we should take into account that CFI divided by sigma A is again an average one. So, because it would be changing during the time as a function of time. I said, if you look to the shape of the flux and so on, it is endless level. So, again, here sigma A, total loss term, consists of fission and absorption. So, next one, uranium-236, here called N2. Again, that is the last term here, but here we don't find for it not sigma A, that means not A, here sigma A, we find that one only. That means we go this way, because uranium-236 is formed by this way, and it is lost only by this way, or by this way only. So, and you see here for uranium-236, production term, that means from here, the two, not fission part. That will be production term, and that will be the last term I said before. You see here, cross-section is N gamma. That means capture, only capture. Good. So, if we go back to the first equation for uranium-235, then it is very simple to solve it. It's an exponential function. See here, and then you can put here, insert here for N1, and you would get, of course, the solution for N2. So here is, I said before, 2, phi sigma F or phi sigma A is a mean value. For this reason, that means mean value of, because everywhere you find the product of phi and cross-section, this product is all the time, or the mean value for this product is needed everywhere. For this reason, you see the bar and at the top, because the mean value for that value. Or here for F and for capture or absorption. So now you remember we defined by this process in one case, absorption, or here in case of the absorption here too, by this way, N gamma 2, by this way, we lose this nuclide. And the main part of this interaction or reaction is fission. And by fission process, we produce the energy. But for this reason, we have to define a unit. We did it in the first semester too. We have to first to find out how big is the amount of the fissions during the operational cycle, for example. The unit for it, or the symbol for that one, is B, burn up. So, and burn up is defined by this way. You see here, under the integral sign here, the flux multiplied fission cross-section, macroscopic one, that means the same like here, but for fission. So that is then at the time t, But a cycle is very long, for example, 1 year or 2 years. For this reason, this product produced per second has to be multiplied by delta t time interval and then integrated for the whole length of operation. They're called tau. So that would be total number of fission we have made during a cycle. So, but important is in 1 cubic centimeter fuel. In 1 cubic centimeter fuel. Okay? So, because the macroscopic cross-section is this product here. And here N is number density in 1 cubic centimeter. For this reason, here we show this number. I have to take here power supply. So, good. So that is the fission rate in 1 cubic centimeter in the fuel. So, and we know with every fission process, we produce a given amount of energy, 200 MeV, for example. This ESP is exactly energy produced by one fission. That would be the whole energy we produce in 1 cubic centimeter of fuel. But what is the energy? Energy unit is joule, for example, or watt second is the same, or megawatt second, or megawatt day. That means a power multiplied by time. That is in 1 cubic centimeter. If we divide it by the mass or weight of 1 cubic centimeter fuel, then it would be the energy produced in 1 cubic centimeter of the fuel per gram of the fuel. Because this rho is density. It is the mass per cubic centimeter too. So the numerator here is the energy produced in 1 cubic centimeter. Here, denominator here is the mass per cubic centimeter. For this reason, this one is in kilogram or gram or tons, and the numerator here is, in this case, is the energy. Watt, second, or joule is the same. So, for this reason, if you put here the average flux or average mean value for this product given here, then it can be integrated. The integral of delta t for the whole operational cycle would be tau. Finally, you get for burn-up due to the fission, the burn-up would be then disturbed here. But again, the unit here is megawatt or watt second per gram or kilogram fuel. So, you remember there was other unit for fuel consumption. Here, other unit is fission per initial metal atom. Metal atom means, in this case, heavy metals. Heavy metals contains or consists of all fissionable and not fissionable fertile material. For For example, plutonium or neptunium is heavy metal, but not fissionable. Uranium-235 is fissile, fissionable, as well as that, or contains as heavy metal too. So, okay, fission per initial metal atoms. So, you see, numerator here, that is the number of fission during the whole cycle, fission whole cycle, in 1 cubic centimeter, of course, but divided by the number of heavy metals, heavy metals in 1 cubic centimeter too. Sm means heavy metal. So, number density heavy metals can be calculated from the physical density of heavy metals. You remember, rho multiplied by Avogadro number and then divided by atomic mass. See here, L divided by M atomic mass. If you replace, then this relationship goes to this one, and this term means there is a relationship between FEMA, that means fission per initial metal atom, and burn up is the unit megawatt day per tons, or megawatt second per gram. That is only conversion factor between them. And all these are constants. For example, M is fissionable material or heavy metal, in this case, something like 238, and Avogadro number available, energy per fission available, so that these all terms can be calculated and goes to that. So, but I would like to have your attention to one point. It is very important. This definition is, or even last definition, where was it? Here. See, burn up. Megawatt day, numerator, divided by gram or kilogram or tons heavy metal. Important is here, you see flux and sigma F. One has to put here the mean value. If you operate the reactor 1 or 2 years, then because flux would be changing as we saw before, then we need average value, not the initial value. A lot of people make this mistake. Good. We found out the relationship between two different units, and there is one additional unit called FIFA, fission per initial fissile atoms. Fissile atoms are, I said, fissionable material, uranium-235, plutonium, and so on. That means in this case, if we have a PWR core, then mainly fissile is uranium-235. And you see here that it means the difference between initial heavy metal, M, and fissile uranium-235 is only the enrichment. For this reason, the relationship between FIFA and FEMA is only this term. That means number density heavy metal, all uranium, plutonium, neptunium, and so together. And this is initial number density fissile, that means fissionable, uranium-235. And you remember, number density fissionable material divided by number density of all heavy metals is called enrichment. For this reason, relationship gets FEMA divided by enrichment. Why divided by 100 is because this is then the absolute value, and normally the enrichment is given in percent. But for absolute value, one has to divide the percent in 100 in order to get the absolute value. That's it. Example, very typical value for enrichment, 3.5%, uranium-235. And from here, you can calculate B. So B megawatt day per tons. It is then at the end of 1.5 years operation, depends, of course, on the type of reactor. So then if that is the megawatt or the burn up in this unit, for example, if you know the reactor has 2,000 megawatts power and it has been operated for 1 year, then it would be something 1 year means then one had to multiply 2,000 with the 1 year in days. Then it would be then megawatt day. So again, that would be the megawatt day per tons, of course. What I said is the total energy produced, not the energy produced per tons. That is for whole reactor. 2,000 megawatt is produced in the whole reactor. But this unit is per tons. One has to know exactly how many tons are existing inside the reactor. And the total energy divided by total mass would be then per tons. Okay. The starting point is B, is given. Anyhow, doesn't matter how, is given. The question is, how big is the FEMA in the other unit? It is very simple. Putting here, you can get here. This number in FEMA and in FIFA would be the other unit according to that one. You see here because the enrichment is available. Yeah. Here is very small point which should be then considered too. The power we produce, megawatt or in any unit, it is not the electrical power. That is the power totally generated by the fuel. That means it consists partly of the normal heat. So, and the relationship between the electrical and the total energy production is called then here the efficiency, eta. Good. I guess you know this table or this very small calculation. They burn up how much energy produced per unit fuel. If unit fuel is fissioned, how much energy? If you take 1 gram uranium-235 fissile, fissionable material, on fission, how many atoms? Avogadro number divided by atomic mass would be so many atoms. Energy per fission, 200 MeV in joule would be 3.2, 10 minus 11. 1 gram consists of so many, then 1 gram would be then this numbers, atoms. Every fission, this energy, totally so much joule would be produced if 1 gram uranium-235, not fuel, uranium-235 is fissioned. So, joule means what second here, and then if you divide it by the conversion factor between second and day, is what? You get the unit, the result in what day. It was what second, now is what day. If you divide again by 10 power 6, you would get in megawatt. That means 1 gram, uranium-235 again, efficient, you produce approximately here 1 megawatt day. That is only just for orientation. So, now, you remember this chart, many nuclides, and we saw only for some part of them. Now the question is, it has to be solved in very general. You see here, again, a set of equation, differential equations. And if you start here, for example, with thorium, some reactors are loaded with thorium. So thorium goes to, by absorption, capturing a neutron goes to thorium-233, then it goes to here to thorium-234, and protactinium, and then going to uranium-234, and then uranium-236 by absorption and neutron, and then the other pass goes here is the way as we discussed before. That means in the whole process of this fission, many nuclides are involved. And for this reason, in general, the equation can be written in this form. That means first starting nuclide, second one, third one, fourth one, and so on. And we should take into account that every one depends on the nuclide before, not as a result at every time step. See here, the change of the nuclide N2 within delta T depends on the value of N1 at this time step, not here the result at the end of cycle. For this reason, the only way is solve the equation and this as a function of time, and then put it here, and in order to be able to solve for N2. So, but at the same time, one has to take into account that phi would be changing too. And this is possible only by a very complicated calculation. That means there should be other, for example, diffusion codes, which allows to calculate the flux distribution as a function of time, and for every time step, the result from there can be used here. So, good. And in the whole paths or channels you saw before, higher isotopes and so on, some could be only isotopes which are on the decaying type, not by absorption and so on. For example, here number 7 is produced, for example, if number 6 is decayed and this one is produced, but there is no loss term for that one because maybe the cross section is so low that it doesn't have any impact or effect on the change of number densities. Good. Now I would like to continue then with the next step. Please. So the next one is uranium-238. Remember what happens with uranium-238? We discussed about that. On the scheme, on the table, you show here uranium-238 capturing neutron, going to neptunium, decaying, going to plutonium as fissionable or fissile material, going to plutonium, and from plutonium, capturing neutron to plutonium-241. So, and then to americium here, 241, and plutonium-240 by absorption of a neutron, plutonium-242, and finally to americium, curium, and so on. I said before, they are then minor actinide with very long half-lives. So, in equation, we discussed about that. So remember, that is exactly the path starting from uranium-238 to plutonium-242. So, this way, at least by analytical way, we know the concentration of the individual nuclides in case of actinoids, for example. Now, but during the fission process, some fission products are produced, and the characteristics of the fission products are important too for neutron population, for behavior of the reactor. For this reason, exactly in the same way, like for the actinide, the inventory of the fission products and concentration and so on should be determined. So, and you see here in this table, characterization of some fission products, here krypton, for example, going to here to cesium and so on, iodine, everything is here, can be taken from this table, and we know how big is the inventory during the normal operation or during a cycle. The unit is old one, Curie, but you can find here how big is, which one has the biggest and among the fission product, of course, biggest activity. The radiation type, you see mainly you find here in case of fission product, you find beta emitter. But in case of actinide, you saw more alpha, they are mainly alpha emitter. And here the energy of the individual photons or rays produced. And finally, you find in this column here, the half-life, and you see compared with the half-life of minor actinides, for example, or here actinides is short. But you find here some, for example, here, cesium 137, it is a big one, is with 30 years. So it is different, or if you take here strontium here 90, then is here long too, 28 years. Compared with minor actinides, seems to be short, because it is relative to that one. That is the characteristic difference between fission products and here actinides or minor actinides is long half-lives. Good. In case of fission product, the equations describing the balance is similar to the equations for actinides. But we discussed about that fission product as a result of the fission process. And we see here, doesn't matter which one, we find here the index I for any fission product. So one thing is fission products, doesn't matter which one, absorbs neutron too. And xenon, for example, has very high cross-section. if it absorbs neutrons, it would be lost. And you see here, absorption of that nuclide, that means this fission product, with the existing flux would be lost here in the balance equation. So the other one, every fission product is a radioactive material, half-life and so on. That means gets lost with the decay constant lambda I, multiplied by with its number density. The same like here. Good. Now, everything was lost there. But this nuclide is produced by different processes. One is as a result of other decay process. For example, if we take the precursor, I-1, for example, if we consider here xenon, the precursor is iodine. That means Ni is xenon, and I-1 is iodine. Iodine J is here, iodine. So, if iodine here, Nj, it decays with the decay constant J, the result of this decay, iodine, is xenon. For this reason, a plus term. That means this fission product or this radionuclide could be the result of a decay of a precursor. That is the source term, the other source term. This one. Imagine any nuclide here. If one nuclide, for example, strontium 89, if it absorbs one neutron with this cross-section under this flux, then instead of strontium 89, strontium 90 is produced. For this reason, this is then cluster. Again, this production was because of the decay of that one, and this production term because of the absorption of other nuclide going to this isotope. Finally, and very important term is in this balance equation, production of this radioisotopes or fission product is fission yield, because every fission product can be produced, as the name says, as a result of the fission process. So, but if we make 100 fissions, many or different fission products are produced. One of them is Ni, and that would be samarium, xenon, molybdenum, different. Everyone, as a result of a fission process, takes place by a yield, fission yield. And the fission yield, for example, gamma I. For example, if we take iodine and we make 100 fission, something like, or 1,000 fission, something like 6 iodine isotope or isotopes would be produced. And this gamma, the fraction of this nuclide from fissioning of 100 fissionable material is called fission yield. Well, this integral here is, again, the number of fission we make in the fuel. Number of fission, but during a cycle, we have different fissionable material, fissile. For example, uranium-235 and partly plutonium-239 produced from uranium-238. For this reason, the fission rate here has to be made or has to be calculated for all fissionable materials, K. And if we take, for example, uranium-235 only, that means K is uranium-235, then this is then fission yield for that fission product as a result of the fission of uranium-235. So that would be the whole production term due to the fission process. You see, for radioisotopes or for fission product, the equation is similar to the actinide ones. And you see here, as a result of the fission, as a result of capturing neutrons by other isotopes, by decaying other or precursor going to this nuclide, by the last term would be because of the decay of that radionuclide, and last term because of its absorption of neutron. So this equation can be easily solved. So now depletion and conversion. Now we are going to be more realistic and to see what happens with the fissile material, for example. You know, the operation of the PWR or BWR is based on the use of uranium-235 with an enrichment something like 3.5%. So the question is, how much is the concentration of this material would be reducing? So this is uranium-235. You remember 2 is coming from the number Z number, and 5 is coming from the atomic number. 92 and here 235, the last digits. So that is the change of the concentration per second, uranium-235. Right-hand side is, again, we have only one term, last term, because of the here capturing neutron. Because of capturing neutrons. That means fission and absorption. You see here too, uranium-235 is lost because of the fission or because of neutron absorption. Good. Now, you remember that is, I repeat everything from the last semester. If you take the phi, neutron flux, to dt, then you get d theta. D theta means, in this case, neutron fluence, not flux. Fluence is flux multiplied by t time. So, and then this equation gets this shape, and you see here it is very simply solvable. The solution is an exponential function. Don't forget here again, sigma 25 is here capture cross-section, fission plus absorption. And so now the question arises, what about the neutron, here the nuclide uranium-236 here? Coming out because of the here absorption process. What about that? So in this case, we have the equation is like here. We have production term, that one, and minus term. Minus term is because this nuclide, uranium-236, absorbs neutrons and gets lost. or goes to uranium-237. So for this reason, and it is proportional here to its concentration and absorption cross-section for this process. Good. But production term. We know, according to this scheme, that uranium-236 is produced not by fission way, produced by absorption way. This one, or total loss of uranium-235, was the total loss due to fission and due to absorption. For that one, production of this one, we need only the absorption line. For this reason, you find here the same value as before for uranium-235. That is the total absorption in uranium-235, but multiplied by this ratio. And this ratio is the fraction of the capture, the fraction of the absorption to total capture. It means only this branch. This is defined, this is alpha 25, defined fission to capture. That would be the solution or equation, production term for differential equation uranium-236. Now, that is the main parts, because along this chain here, uranium-235 is the first one, uranium-236, and then the following nuclides. So this can be solved too. We solved the first one, you remember? And this solution can be put in 25, can be put here, and then we get an equation only for uranium-236, and it can be solved. The result would be that one. So that is for uranium-235. This is for uranium-236. And you see, it depends on the initial concentration of uranium-235. And it depends on the individual cross-section for absorption uranium-235, and it depends on alpha value, and I said it is the ratio here, capture, here absorption to fission. So you see here the same process too, uranium-235. For uranium-235 is similar way. So this example, you remember we solved during the first semester, but it is better to repeat it again. Calculate the burn-up of the fuel for a reactor of approximately here 700 megawatt thermal for a period of 1 year. And you remember, heavy metal content is given here, 47 tons. Neutral flux is given, this number, and absorption cross-section for uranium-235 is given this number. So now the question is, we have different ways, or the first estimate, you remember, that is exactly, we should pay attention to it. It is only an estimate. You remember 1 gram equal to fission of 1 gram uranium-235 produces 1 megawatt day. So, good. The power is 700 megawatt, operated the reactor for 365 days. The total megawatt day would be that one. The uranium-235, the need for it is 1 per gram per megawatt multiplied. That would be this number. So per year. And because it is natural uranium, not enriched uranium. For natural uranium, that means uranium ore, is 0.7%. You remember in the beginning I said? That means if you divide this number, total amount of uranium-235 needed for 1 year operation, and divide it to enrichment, we get the amount of uranium as heavy metal, uranium needed for 1 year. That would be, of course, more than 36 tons uranium fuel for 1 year operation. For 1 year operation, only 0.25 tons uranium-235 is needed. But total uranium is 36 tons because of the relationship with enrichment. So, okay, now burn of a megawatt per tons heavy metal, so many uranium-235 we need, divided by the initial mass of heavy metal, 47, was given somewhere here. You calculate from there, megawatt day. Okay, we calculated before, megawatt day divided by 47, then you get, burn up in this unit. So if you have done this, then FEMA is this way. You can calculate it. So, and FIFA can be calculated. But please pay attention to that. This is very approximate way. It is not very correct way because everything is changing. During one cycle operation, phi is changing, for example. Material composition would be changing. The question arises, which one should be applied? The answer is, of course, the mean value, if you know it. So that should be kept in mind. Now, we have second method, but in other units. Neutron flux or fluence. Fluence is flux multiplied by time. Flux is given, this value. Time is 1 year and second given. You calculate the numbers. That will be fluence in this unit. So then, that is the cross-section for capture. You remember, it is given. Cross-section, I guess, here is given. Absorption means here fission plus capture plus absorption. This should be capture. So, okay, that is the flux, that is the cross-section, and this is the number here, fluence. If you multiply together, you would get this number. And this value appears in the exponential function. You remember? We solved the equation here. That is the amount of the uranium-235 after or for a fluence of theta. That is actual concentration. But how much has been consumed or lost is this value, actual value, minus the initial value. And exactly that is called delta. So for this reason, you find here delta, and delta is exactly 1 minus this exponential function. It means this one minus this term, the 0, only this term. At the right-hand side, it would be, for the left-hand side, it would be delta, and for the right-hand side, it would be 1 minus this exponential function. For this reason, you see initial mass for the consumption, mass of the, or consumption amount of the uranium-235 loss due to the absorption. We get here initial mass multiplied by this 1 minus exponential function. Yeah, you put this number here and calculate it, finally you would get 0.754. That means 75% of initial mass of uranium-235 would be lost. 75%. You see, that is completely different unit in percent. But previous steps have been in FEMA or FIFA, or initially by megawatt day per tons heavy metal. Now, I would like to explain this third way too. So, first, I would like to start, you can say that is the third way. So, we have seen here the delta M for uranium due to the fission. We saw due to the fission, only due to fission, not because of absorption. Delta M, uranium-235, divided by initial mass, uranium heavy metal. Uranium or heavy metal, not uranium-235, would be the consumption or the lost amount is initial mass uranium-235 minus initial mass after 1 year divided to mass, again, heavy metal at the beginning. Good. You remember, this is a difference. And the difference is exponential function. You remember, we saw that before. Exponential. But here for uranium-235, this is due to the total capture. That means by absorption and by fission. So it means in case of the wave, only by fission in order to produce energy. Here, not the sum of two should be taken, only sigma F has to be taken. For this reason, you see here, again, the same exponential function, 1 minus exponential function, but here only for this exponential value or function here, you find sigma 5, that means uranium-235, but only fission. Only fission. So, and you see here, then M5, initial value, and this is M, heavy metal, on the initial condition. So if you divide numerator, denominator by initial mass, then you would get, for example, if you take only for 1 cubic centimeter, then you would get here 1 plus N uranium, number density uranium-238, initially divided by initial number density uranium-235. Again, this one is M0 uranium-235 plus M0 uranium-238. Then you divide the numerator and denominator by M05. The result would be exactly, because mass is proportional to number density, you would get here 1 plus N80 divided by M4. Okay. Now, please take into account that this ratio we are calculating is not the ratio for loss term due to the total absorption. It is only by fission way because of that sigma here, F. Now, if you put for sigma value here, fission, please pay attention, 580. In the previous case, you remember, sigma was 671 because this is the total fission plus capture. Here is only fission 580. The flux is given, this number 6.68 power 13 multiplied by T operational time, 1 year, days, hour in hours, and second, hour and second. So, and here is the numbers, number density uranium-238 divided number density at initial condition, number density uranium-235. And we know, so this value is, if you write here then N5 plus N8 divided by Ny, it would be 1 over only 0.03. I should emphasize here, this is now 0.03 is for enriched uranium, that means 3%. For natural uranium, then this number should be 0.007. Remember, as in here. But this is other case, similar case, only not for natural uranium. It is for partly enriched uranium with 3% enrichment. So, if you put the values here, you get 0.0211. That is, we have gone back to the definition of FEMA. FEMA was number of fission per initial metal atom. That is number of fission, because you remember we used the fission, number of fission per initial metal atom. For this reason, this is the value for FEMA. So, that is one thing. The other point is, now, we should keep in mind, we went here directly the analytical way and calculated, by calculating the fission rate and so on, calculated directly the FEMA, not by using the relationship between megawatt day per tons and so on, directly by using those values. Good. That is one aspect. Now we go back to other case, to other unit, megawatt day per tons, heavy metal. How to get it? To get it, as here the factor says, megawatt day. That means we have to take here number of fission, you see here, by sigma F n number density. These three terms gives number of fissions per cubic centimeter. So per second, the whole 1 year multiplied would be the whole number of fissions in 1 year. And in every fission, we produce epsilon energy, 200 MeV. That would be the total energy we produce during 1 year cycle in 1 cubic centimeter. In 1 cubic centimeter. Now, if we divide it by the mass of 1 cubic centimeter by heavy metal, rho, physical density, then we get exactly in megawatt day per ton. So, now for your information, N number density again, uranium-235, number density heavy metal. Number density heavy metal can be calculated very easily. That is physical density, sorry. Number density can be calculated is or relationship between here physical density and number density of heavy metal, which contains mainly of uranium-238, is, again, this rho, physical density, is equal to number density multiplied by atomic mass, 238, and divided by N. Okay? So, now, you see here, this value, N8, number density uranium-8, number density uranium-235. What is the ratio here? Ratio is representing or related to the enrichment. The enrichment, for example, in this example here is 3%. Can be put there, and if you calculate it, you would get 34,100 megawatt day per tons. So, and you see one very clearly that in this case, the relationship between here FEMA and megawatt day per tons is not the number we had before. See here, megawatt day per tons, FEMA is 110 power minus 6. Here is not the relationship or the factor between is not the same. So the reason is, here is something different. Why? Because here, this way of calculation of megawatt day per tons assumes that flux is constant, and here sigma is constant, n is constant, and then calculated here according to the initial value. But, and this one is the, here is assumed the total fission rate is that one. And assuming again, phi is constant, n is constant. But in this way, if we look to in this way, that was the initial mass uranium-235. That is initial mass uranium-230, not initial mass of uranium-235. At the end of 1 year, the difference is due to the fission. That means the difference is exactly the same, or the same should be the same term, because here is the last term due to the fission. That means this term here, the correct one, because we have solved the differential, this one, or this term here is replaced by this simple term. That is not correct. That is an estimate value. For this reason, the relationship, I said before too, this number here is just only for between B and FEMA, in megawatt day per tons, is a very simple one. It is not all the time the same. For this reason, in order to come, again, to come to megawatt day per tons, in the numerator here, this value should be taken. That is the change due to the fission. This value should be multiplied with epsilon. And then dividing by this term and getting the result. If you go this way, as we so here, remember, you would get for FEMA, you have obtained for FEMA this number, and you would get for megawatt day per tons heavy metal, you would get something like 2.4, like here, 2.4 10 minus 6. That means the same factor multiplied by this value. That means the calculation of the B value, according to this unit is not correct if we take for the numerator only very simple term according to that one, because phi is changing according to exponential function. Again, that is new one compared with the our way in the past. In order to calculate the megawatt day, only in the numerator, not the simple term, this term should be used. From the other side, for your information, if this three factors here on the exponential function is very small, that means exponential value is very small compared to 1, then this whole term in the numerator gets the same shape like here. I would like to summarize. If you want to calculate, then here burn up in unit megawatt day per tons heavy metal. Numerator should be according to this way. Yeah, according to this way. And then multiply with epsilon. That would be the whole energy produced. So, good. So, I hope it was understandable. Now we go to the second step. If you, because it takes slightly more time, I would like to propose to make 5 minutes or 10 minutes break, and then we can continue. Yeah?